Take 3. Once again, here is the Ohm's law wheel, or Pyre wheel, showing all the 12 formulas that can be derived from the voltage triangle and the power triangle. Now you might notice that along the left here, under the DC column, we have a list of all the Ohm's law formulas from the Pyre wheel, and they will match the AC resistance Ohm's law rules for AC, and for the other formulas, you can think of them as solving for the certain side of the triangle. So we have a power triangle, our impedance triangle, of course, and our voltage triangle. And you'll notice that the formulas will match. So if we want to solve for the reactance side, the XL in this case, it's the same method as we did over here, but instead of E over R, we're using EX, or the voltage drop across the inductor or capacitor, divided by the reactance in ohms. How do we get reactance? We can use a formula. XL equals 2 pi FL. And XL in this case is inductant reactance in ohms, not to be confused with inductance, which is henries. F is the frequency of the circuit in hertz. So if it's a 60 hertz circuit, we'll use 60 hertz. And of course, L is the inductance of the circuit in henries. Multiply those together with the values, we can figure out our XL. If our frequency goes up, so does our reactance. If our inductance goes up, so does reactance. So this is directly proportional. For capacitive reactance, we have the formula 2 pi FC, and XC in this case is our capacitive reactance in ohms. F, once again, is the frequency of the circuit in hertz, and C is the capacitance of the circuit in farads. Now, a lot of times we write microfarads for capacitance. We do the math, though, using farads. In this case, it's inversely proportional to frequency, so if our frequency goes up, our capacitive reactance will go down. Okay, also if our capacitance goes up, our capacitive reactance goes down. In a purely resistive circuit, this would be the same for DC, but in this AC circuit, we can see that when our voltage peaks in AC, so does our current. So they are in phase. Also, our power peaks at the same time. And you'll notice as the waveform goes to 0, we have 0 power. And also, when we go negative, we'll have negative current and negative voltage. We still have positive power. We can represent a purely resistive AC circuit as a vector on the 0 axis. And here we have a purely inductive circuit. This is a theoretical inductor. Most inductors do have some resistance, but we'll look at those later. But a theoretical inductor, we can see here that as our AC voltage peaks, our current doesn't start to rise until 90 degrees after. So it lags our voltage peak by 90 degrees. And so does the P. In this case, it is not true power, although it's represented by a P. This is what we call wattless power, or VARs, also known as volt-amp reactance. And of course, when our voltage goes negative, we could have positive current, so we have negative VARs. So this isn't doing any work. So it takes away, gives back, takes away, and it still consumes amps and takes power from the supply, but doesn't do any work. We can represent the purely inductive circuit with an arrow pointing down or up, but we have to pick one direction, doesn't matter. And here we have a purely capacitive circuit. You can see that the current leads the voltage by 90 degrees. We can represent this purely capacitive circuit with the arrow pointing up, which is the opposite direction as the inductor. They are 180 degrees out of phase from each other. In a practical inductive circuit, it will have some resistance and some reactance. Generally a lot of reactance, because that's what they're designed for, but because they're basically coils of wire with an iron core, the wire does have some resistance. We can represent a practical inductor with our impedance triangle, and we can see that we have some wattless power, but we also have some watts. Voltage times amperage gives us watts, and it's not out of phase by 90 degrees, it's out of phase by a value that we can find by doing the cos, or the inverse cos of the angle. We can solve for the different sides of the triangle using Pythagorean's theorem, or trig if needed. So here's an example. 120 volts, 4 amps, 24 ohms of resistance and 18 ohms of reactance. First step would be to draw the vectors, because that's what we're doing, we're adding vectors. And then we can decide which triangle we can use. So there's 3 for the series circuit. We can use voltage, impedance, or power triangles. But basically all we're really doing is adding vectors. So we could also go on our calculator 24 at angle 0 plus 18 at angle 90 and still get the same results. Here's our triangle. Fill in the values. Using Pythagoreans, we can see that it is 30 ohms. And then we could do a check. Is 120 divided by 4 30 ohms? And if it is, we've done it right. We could also find the voltage. 4 times 24 will give you 96. 4 times 18 will give you 72. But don't fall into the trap of adding those straight up, because they are not in phase. But we can add them vectorially using the voltage triangle. And if you do Pythagoreans to check, you will see that we will get 120. We could also go straight to power. We could go I squared 24 to get 384, I squared 18 to get 288, or we could go 120 times 4 to get 480. This is a good way to check to see if your math is correct. The best way to describe power factor of a circuit is the cos of theta, which equals watts over VA, but you can also use R over Z, or ER, over here, they use VR, either way, over EZ. If you do the math, you'll find that all these numbers will add up to 0.8 because it's the same circuit. The power factor will be the same throughout the different triangles. We can also solve for the angle by inverse cosing the power factor, and we can use that cos to the -1 button on your calculator to do so. We can get 36.87 degrees for our angle lagging in this case because it is a inductor. The same method can be used to solve for series RC circuits where we just have both resistance and capacitance. Now we'll have a look at a series RLC circuit. Once again, we have these triangles at our disposal. And all we're really doing here is adding vectors. We can go 6 at angle 0, which is our resistance, 6 at angle 90, which is our capacitance, and 14 at angle 270 for inductance. When adding vectors, we place our vectors head to tail. So there's a resistive vector, inductive vector, and our capacitance reactance vector. And they are out of phase by 180 degrees. So it doesn't matter how you draw them. There is no real standard, just that once you pick a direction, the other one's the opposite. So we can get our net reactance by subtracting one from the other. So generally, common practice is anything above the zero axis would be in quadrant 1. That would be considered leading based on phasor rotation. And anything in quadrant 4 would be lagging with our base zero vector considered the starting point. But it really doesn't matter. So once we subtract XC from XL, we get a net reactance. In this case, it ends up lagging. Now, if you do the math and you end up with a negative XL, it doesn't matter, because when we square that value to get the Z, it will still be a positive value. Here we are, 10 ohms. We could also, or 10 ohms. 120 divided by 12 here would also give you 10. And once you find Z, you can find the rest of the missing values of the circuit. We can use the 12 amps to get the 72 volts here, 72 volts across the capacitor, and 168 volts across the inductor. And you think, well, how can that be possible? It's higher than our source. Remember that they aren't in phase, and they must be added vectorially. And you could check your results by using the voltage triangle. One last little thing. In an RL circuit, there's a frequency, an RLC circuit, there's a frequency when inductive reactance and capacitive reactance are equal. This is called resonant frequency. In a series circuit, the current will be at its maximum. And if our resistance is really low, we would have a really high current, so it would normally be avoided. High resistance is not as big of a deal. In a parallel circuit, if we are at resonance, the current will be at its minimum, and sometimes this is desirable. This is also known as unity. You can calculate the resonant frequency of a circuit using the resonant frequency formula. And the formula is divided by combining two reactance formulas together. So at resonance, if XL equals XC, then 2 pi FL equals 1 over 2 pi FC. And through the magic of transposition, we can solve for F and come up with this fun guy. And that's it for now. Next up, we'll look at RL and RLC circuits.